Hello, everybody. So what we're going to be doing today is I'm just going to go through and solve the problems in the spring 2021 exam 3 practice test. Um, I wrote 2020 here as well because I think the document is actually labeled spring 2020 exam 3, even though of course it's 2021. So yeah, let's just get into it. There are other written solutions to this. So this is mostly just if you want to watch a video. So let's see here. Problem one. Oh, so we have a graph, which I guess I have to draw here. If I'd been smarter, I would have not done this. But okay, 1, 2, 3, 4, 5, 6, 7, 8, 9. We have a bunch of edges here. So let's see. Um, like that, like that. There's two more here. There's one here. There's one here. Uh, there's one here. There's one here. Is that it? That's looks close. Maybe that's it. All right. A, B, C, D, E, F. Really? G, H, I. What kind of numbering is that? Okay, so let's just double check here and make sure that everything looks like the right number of edges. I think that's correct. Okay, so what are we supposed to do here? So part A is number of vertices, and part B is number of edges, and C is the degree of each vertex. Okay, so let's just go through and answer these. So I guess first of all, for the number of vertices, you're literally just counting them, right? So you just go 1, 2, 3, 4, 5, 6, 7, 8, 9. Oops, 9. Then you want the number of edges. You do have to count those up. It's a little bit tedious. So makes sense to kind of like cross them off as you count them, so then you don't count them twice. So like, let's see here. So there's 1, 2, 3, 4, 5, 6, 7. We already counted this one. We already counted this one. 8, 9, 10. Is that 10? I'll count again. 1, 2, 3, 4, 5, 6, 7, 8. Oh, 9, 10. 11? Oh, man. Okay. Complicated. Counting is hard. Back up. Oops. I mean, you get the point anyway. But, okay, so let's see here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Is that right? 10? Okay. You know what? We're going to find out in the next step anyway. So, oh man. Why is it doing that? That's frustrating. Okay. I don't care. Um, so maybe 10, maybe 11. Uh, I don't know. Let's count the degree of each vertex. So the degree of each vertex is easier to count up by hand because you're only looking at one vertex at once. Uh, oh, I lost an edge here. There's supposed to be one from A to C. Well, that probably changes things. Okay, anyway, let's just do this and then we'll see how it goes. So when you're counting the degree of each vertex, you're just counting the number of edges out of the edge. So 3 there, 2 here. For C, you've got 1, 2, 3, 4. For D, you have 0. For E, you have 1, 2, 3, 4, 5, 6, it looks like. For G, you have 1, 2, 3, 4. For H, you have 2. And for I, you have 1, 2, 3. Okay. And so technically the way to write these is like this, like degree A 3, degree B 2, degree C 4, degree D 0, degree, I'm going to be smart here and just duplicate this. So D, E, G, H, I. Okay. E, F, G, H equals. All right. So we can just put the numbers in that we already found. So E was 6. F was 0. I didn't write that. G is 4. H is 2. I is 3. And by the way, if you add these all up, right, so let's just add these up real quick. It didn't ask you to, but sum of the degrees, 3, so 5, 9. So we're just adding these numbers up. So 5, 9, 15, 19, 21, 24. Wait, really? If there's really 24, then that means there must be 12 edges. So I counted wrong. Okay. Oh, that's just killing me. Stop it. Why can't I just delete that one thing? Okay, did it. All right, so if you count up the number of edges, it must be 12. I can't count because my drawing's too ugly. I guess we could delete them all. That's one way to do it. Haha. No. The way I normally do this by hand, by the way, is with like a highlighter or something. So you go like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, there is 12. That's really bad counting on my part before. Okay. So that's that. Problem 1 down. Problem 2. That's probably the most tedious, I think. I hope. So for problem 2, the problem statement is basically trying to give you a theorem that's given in the book, and also we went over in the lecture. But basically, the number of edges is related to the degree, right? We just said it, right? Like the sum of the degrees of each vertex, sum of the degrees of each vertex is equal to 2 times the number of edges, is the way they write that. Okay, so so part A says, can you have a simple graph with, and when it says with, it means consisting. I should have, that's bad language. I should have said consisting entirely of. but I said with. Can you have can you have a graph with 7 vertices of degree 5? And what I meant was, could this be the degree sequence? 7 vertices of degree 5. So 1, 2, 3, 4, 5, 6, 7. And the problem with that is if you check the sum of those degrees, the sum is going to be 35, right? Because it's 7 times, there's 7 5s. So the sum is 35. So by the theorem up here, the sum of the degrees should be 2 times the number of edges. So 35 is twice the number of edges. But that's impossible because 35 is not an even number, right? So how could it be? It's not twice the number of edges. But 35 is odd, so that's impossible. Right? And so because of that, then no such graph could exist. So no graph with that degree sequence exists. No simple graph, I should say. Okay. And so that's really what it boils down to, is that the sum of the degrees cannot be odd. So when you get to B, we can do B much faster. They say 8 vertices with degree 3. Right? So again, that would be 3, 3, 3, 3, 3, 3, 3, 3. And there, the sum is, of course, going to be 3 times 8, which is 24, which from the theorem would imply 12 edges, which is fine. Because it's not odd. Or sorry, oops. Which is fine because this is not odd. So, yes. So what's the point? Yes, that graph could exist. And you could draw it if you wanted to, but, we didn't. So that's all there is to it. It's just asking you if the sum of the degrees is going to be even or odd, because odd is not allowed and even is. All right, number 3. So number 3 is we're going to be drawing a niche overlap graph. So the bird species we have is hermit thrush, which I think I'll just write thrush. Right, so it says hermit thrush competes with the robin and the blue jay. So you have thrush, robin, blue jay. And when they say it competes, right, in a niche graph, what you do is you just draw an edge between each vertex where the species compete. So when they say hermit thrush competes with the robin, you just draw a line there. And with the blue jay, then you draw a line there. Then it says the robin also competes with the mockingbird. So we need a mockingbird. There you go. Mockingbird also competes with the blue jay. Like that. And then it says the nuthatch competes with the hairy woodpecker. The funniest of all names. let's see. Robin competes with Mockingbird. Mockingbird competes with Blue Jay. Nuthatch competes with the hairy woodpecker. Where's the nuthatch? We don't have one, huh? So we got to draw that too. The second funniest thing. All right. There you go. I think I got that right. Okay. So you just draw a line between each species that competes, and that's how that goes. Next problem. Problem 4. This is going to be basically the same thing. I think this is a lot of drawing, so let me get some space. So this is almost the same thing as a niche overlap graph, but this is going to be with like phone calls. So every call is directed edge from the caller to the callee. So there's a bunch of phone numbers here, which I'm going to have to write them down. So it says construct the call graph for a set of 7 telephone numbers, which they all start with 555. So I'm not going to write 555. So like the first phone number is 555-0011. So I'm just going to write 0011. There it is. And then the next one is 1211. 1221. Put it there. 1333. 1333. Like that. We'll do one more. 8888. 8888. There. Then we got 2222. 2222. I'll put it there. 0091. 0091. I'll put it there. And then 1200. I'll put it there. And so what we're supposed to be doing, and it says this, is so directed edge from caller to callee. All right. So they say, starting here, it says 3 calls from 0011 to 8888. So 3 calls going that direction. So you go 1, 2, 3. Make sure you can see the arrows because they're directed. All right. 2 calls from 8888 to 0011. So that's 2 calls going back. Wait, is that right? Yeah, that's right. So 2 calls going back. I'll use a different color. So 2 calls going back. 2 calls from 2222 down here to 0091. So 2 going this way. Two calls from 1211 to each of the other numbers. Oh no. Why would they do that? 2 calls to each of the other numbers. Okay, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2. Okay. And then 1 call from 1333, which is here, to each of, and then there's 3 numbers. Okay. Let's pick a different color. Last color, dark green. Okay. So there's calls from 1333 to 0011. So that's over here. 1221. So that's right here. And 1200, which is there. Okay, so I think we did it. Hopefully I got all those. The main problem here is that it's just a lot of edges on the graph, and that makes it hard to draw. But conceptually, it's pretty easy. Number five. Um, all right, so five is not too complicated here. So we have so G has basically degree sequence, and they just list some degrees. So they say 2, 4, 3, 2, 3, and they want to know how many edges must it have. And B, they want to draw a graph. And it's just a possible graph. There can be lots. Um, so let's see here. So how many edges are there? So we already even talked about this, right? The sum of the degrees is twice the number of edges. So add these up. So 2 and 4 is 6, 9, 11, 14, right? So 14. So sum is 14, and that means there should be 7 edges. All right. And we want to draw our graph. So our graph, we know how many vertices it has because we can count here 1, 2, 3, 4, 5. So we have 5 edges. So 1, 2, 3, 4, 5. You don't have to number them or anything, but you can. And then we just start putting in edges. So, it doesn't really matter how you go about this. We'll just be able to make it work. So uh, I'm not going to start with the first one. I'm going to start with the second one here. So the second vertex, which I'll say is B, has a degree of 4, which means if we're drawing a simple graph, it should be connected to all the other edges. 2, 3, 4. So we did this so far. Then what we want to do is start looking at the others. And we didn't have to start there. It's just how I wanted to do it. So maybe C should have a degree of 3. Right now, C has a degree of 1, which means C needs 2 other edges. So I will just draw edges, I guess, between D and E. Sorry, C and D, C and E, just because that's what I feel like that. So now this has 4, and this has 1, 2, 3. So we did that. Now it says D is supposed to have 2. D already has 2. So that's done. E is supposed to have 3. E has 2. E has 2 right now, but also A has 1, and A is supposed to have a degree of 2. So if we draw one edge here between A and E, then now we fixed the degree of A to be 2, and also we fixed the degree of E to be 3. So that graph works. Okay. Now, if you use multiple edges and stuff, it's actually easier to draw graphs like this than if you just draw a simple graph, but we drew a simple graph. So that's a possible graph. All right. So that's done. So the next one is another one that's a pain to draw. And I think I fixed this in the actual exam. So you can thank me for that. Although you won't because you didn't see it the other way. But 0, 1, 2, 1, 2, 2, 1, 0, 3, 2, 1, 0, 0, 1, 0, 2. So this is supposed to be an adjacency matrix, which means each row and each column corresponds to a vertex. So like A, B, C, D, A, B, C, D. And then, so we have a 4 vertex graph. which is going to have a bunch of edges, unfortunately. So I'm trying to have a lot of room here. A, B, C, D. And so the way this is going to work is if you see like A is a 0, that means 0 edges between A and A. And if you see like a 2 here, well, that means 2 edges from A to B, because you use the row first and then the column. So from A to B. So that 2 right there means 1, 2. And we did that. Now, the reason you have to use a directed graph here is because it's not symmetric, which was a homework problem. Right, AB has a 2, which means 2 edges between A and B. But if you look at this one right here, this is BA, there's only a 1 there, which means 1 edge going back. Now, if it was 2 and 2, and this was completely symmetric, so like a 2 here and a 2 here, and if there was a 3 here, a 3 here, right? Like this one is AC, this one is CA. So if those numbers match, like this number and this number, this number and this number, this one and this one, this one and this one, if it was completely symmetric like that, then rather than drawing 2 going here and then 1 going back, we have to, because of these 2 numbers here, we could just draw 2 and call it a day if it was 2 and 2. So we have to use a directed graph here in order to make that a 1. Okay, and so that's what we have to do, and we just keep doing this for all of the edges. So I guess go here. So A to C, there should be 3. All right. A to D, there should be 0. Just cycling through the colors here. We already did BA. Let's do BB. BB is supposed to be 2. Now, I believe in the definition there that actually means 2 loops. But that does vary based on your definition of the adjacency matrix, because some books use a definition where they want like the sum of the row to be the degree of the vertex. And if you count like a 2 like this to mean 1 loop, that works. But if you count a 2 like this to mean 2 loops, like I drew, then, or sorry, 2 here to be a 2 loops, then that means that you ruined the degree thing, because a loop is supposed to count as 2. So 2 loops would count as 4, and it ruins the fact that this is no longer the sum. The sum of this row is no longer the degree of B. All right. Having said that, it doesn't matter. This is just our definition. So 2 loops because there's a 2. B to C, there's supposed to be a 2. Let's pick a different color. B to C. All right. B to D, there's supposed to be 1. B to D, supposed to be 1. C to A, there's supposed to be 2. We did not do that yet. Get a different color. C to A. Picking color's already picked though. That's okay. As long as you can see the arrows. Or not. C to B is a 1. C to B is a 1. Come on. All right. C to C is a 1. C to D is a 0. D to A is a 1. And finally, D to D is a 2. So we got 2 loops on D. All right. And again, that's just kind of a pain to draw, but conceptually it's pretty easy. Problem 7, find the adjacency matrix. Man, we're going to have to split this into 2 videos. 1, 2, 3, 4. And we got loop, 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 loop. 1, 2, 1, 2. Diagonal, diagonal, done. All right. A, B, C, D. All right, and here we want to find the adjacency matrix. All right, so we have to find it this time. So like what we were just doing, but backwards. Also that this is, you'll notice, undirected, which means our life is easier. So labeling at the top here and the side, A, B, C, D, A, B, C, D, that's not part of the matrix. That's just to help me keep track of what is what. Okay, so we're just counting edges here. So you simply go like this, like AA. How many edges are there from A to A? Well, there's 1 loop, right? So that's 1 loop, so that is a 1. And then you say, how many edges are there from A to B? A, B, so none. Also, this is undirected. So if there's 0 edges from A to B, there's also 0 edges from B to A. So if you put a 0 here, you can put a 0 here as well. A to B, B to A, same thing for an undirected graph. All right. Let's go AC. How many edges from A to C? 1, 2. 2. But that also means there's 2 edges from C to A, so a 2 here as well. And then A to D. A to D, there's 1 edge, which means there's also 1 edge from D to A. So the 1 there. Then next row. Next row, B to B. B does have a loop, 1 loop. Okay, next one. B to C. B to C, there's 1 edge. But if there's 1 edge from B to C, there's 1 edge from C to B. So a 1 here as well. Then we have BD. B to D, there's 1, 2. Which means also from D to B, there's 2. All right, next row, we got C to C. C has a loop, so that's a 1. C to D. C to D, there is no edge from C to D. So there's a 0. If there's no edges from C to D, there's no edges from D to C. And finally, D to D, there's a loop. Like that. So there you go. There is your adjacency matrix for that graph. And so those are pretty straightforward. We have another one. You work it out exactly the same way. A, B, C, D. And we have the same thing going on here. A, B, C, D, A, B, C, D. And yeah, we just go and do exactly the same thing as we did before here. So A to A, nothing. So that's a 0. A to B, 1, 2, 3. So there's a 3 there and there. A to C, nothing. A to D. A to D is 1, 1, 1. B to B, there's no loop, so that's a 0. B to C, there's a 1 edge there. 1, 1. B to D, there's no edges. C to C does not have a loop. C to D, 1, 2, 3. And finally, D to D has no loop, so a 0. So those are pretty fast once you're familiar with what to do. And notice from these two examples here that the undirected graphs are much simpler to fill out, and they're completely symmetric, right? So like about the diagonal here, the diagonal is whatever it is, and then on opposite sides of the diagonal, everything matches, right? 0, 0, 2, 1, 2, 1, 1, 1, 1, 2, 1, 2, 0, 0, 1, 3, 3. Those match. 0, 0 matches. 1, 1 matches. 1, 1 matches. 0, 0 matches. 3, 3 matches. Perfectly symmetric for undirected graphs. Okay, 8. And how many problems do we have? Ooh. All right, so we're gonna stop the video after the next problem, which is number 8. 8. Determine whether the graphs are isomorphic. I think this is section 10.3. I'm not 100% sure about that. But we will talk about it right here. So you need to remember the concept of isomorphism, which isomorphism, iso means same, morphism means shape, right? Morph means shape. So isomorphism means same shape. And so really what you're doing when you're checking for an isomorphism is you are trying to determine if the graphs are really the same graph that have just been drawn in a different way. Right? And the way you go about that is you look for differences between them that would show you that they can't be isomorphic. So what you're looking for is look for what they call invariants, which are things that should be the same between them if they are isomorphic, right? So if they are isomorphic, then these should be the same. Right? The number of vertices, the number of edges, and the degree sequence. And stuff like that. And if those don't match, then we move on and we look at other things. So like, first of all, if you count up the number of vertices, right? 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. They're both 5. You're usually not going to get lucky and have that not match. Count up the number of edges. 1, 2, 1, 2, 3, 4, 5, 6, 7. And 1, 2, 3, 4, 5, 6, 7, both 7. Now, if you look up the degree of each vertex, we have 3 here, 2 here, 3 here, 3 here, 3 here, right? And if you look up the degree of each vertex up here, we've got 2, 1, 2, 3, 4, 1, 2, 1, 2, 3, 1, 2, 3, like that. And so when you look at the degree sequences, what you see is that the second graph has a vertex with degree 4. Right? Degree 4 here, this has no vertices with degree 4. So they cannot be isomorphic because those would have to match. So second graph has a degree 4 vertex. And the first does not. This implies not isomorphic. Okay, so that's the kind of thing that you're looking at to see if they're isomorphic, is stuff like that. It's supposed to be the same, it isn't. And you can even get more complicated than that. So you might have to look at things like this. Like this is a degree 3 vertex, right? And this degree 3 vertex is adjacent to a degree 2, a degree 3, and a degree 3. Well, over here, there might be a degree 3 like all of the degree 3 vertices, which are here. You could say, well, is there a degree 3 vertex that's adjacent to a 2, 3, 3, just like this one is? And if you look over here, right, 2, 4, 3, that one doesn't match. And if you look at this one, 2, 4, 3, that doesn't match. So you can get more complicated than just the numbers on each vertex. You can also say, well, is the degree 3 connected to a degree 4 or something like that? That should be the same between both graphs if they are isomorphic. It's hard to show that the graph is isomorphic, and that's why generally you're trying to show that it's not isomorphic, which is what we just did for this one. Okay, that was number 8, and then we're going to stop here and do the rest in the next video. All right. And full recording, and talk to you guys later.